All right. Good morning, everyone. So today we continue to talk about the PN junction, and also we will move to the device. The first device that we will introduce is a PN diode. So last week we have already mentioned that with considering the under the case of the zero bias, with considering the zero bias, we are start to able to understand that there is built-in barriers between the P and N junction, and because of this built-in barrier, that's why that we won't have only pure diffusion mechanism dominate, and because of this built-in barrier, so we will have the induced electric field inside. That's created as a built-in electric field and built-in barrier, and that will stop the diffusion, will be balanced for the diffusion mechanism. So this is a case under the zero bias. And then we start to talk about, in reality, for sure that we will not only consider under the zero bias, we will start to apply the forward and reverse bias. And the most interesting part is under the reverse bias. We can see that the idea, the current voltage characteristic for PN junction is under the ideal case, under the reverse bias, we should have the current approach to the zero. Ideally, we should have very small current under reverse bias. And this is because of the under reverse bias, we can clearly see that our built-in voltage actually is increased, not only the VBI, but also the reverse bias. So also we have to consider the reverse bias here. So also we have to consider the reverse bias under the negative voltage applied on top of the anode. And then the conclusion is that once we have a reverse bias, we can clearly see that our barrier is increased, and because of the increasing of this barrier, that's why that our carriers, no matter for the electron and flows, that would become more difficult to flow to the other side. That's why that we're getting smaller and smaller currents. Okay, so one additional the small concept that we would like to introduce is related to the junction capacitance here. So the idea is that in reality, sometimes we'll not only apply the DC bias. So what we discussed before is mainly we only apply one DC reverse bias. But sometimes with a certain consideration for the electronics, we also will be interested in that on top of this DC bias, we will apply the small AC signal here. So we will consider that there's additional AC bias on top of our DC bias. And with considering this AC bias, we can expect that with a certain period, sometimes we have this DVR, and this DVR depends on the different periods of our AC bias. So in general, now our reverse bias has to consider as a reverse bias plus minus of this small DVR. So that's a consideration in this case. So, and we consider for this DVR, we can start to estimate the capacitance. Because of this small DVR, if we look at for the charge distribution, which we have been drawn before, is rho versus x distance. So we have been seeing in the right hand side, which considered for the typical PN junction. The right hand side, we have the positive charge in the region up to the positive Xn, and also we will have the negative charge up to the space next minus xp. So that's the case we already discussed last time, that we are considering this charge distribution, and later we consider for the Poisson equation to calculate the electric field and then the potential distributions. But we can also use these charge distributions to understand the AC response. As we have been shown here, in this period we have the VR plus dVR. In this period we have the VR minus dVR. So in general, this AC response will lead to the additional charge formation in this region. So this is a contribution coming from this dVR, where will become as a dQ prime here. So with also considering this dQ prime, that means that sometimes we have the charge will become the Q plus dQ prime, and sometimes we have the charge become the Q minus dQ prime, and this additional region we can also consider as a dXn, and this will become the dXp. So in general, based on what we already learned from the last class, in the case of the typical DC bias, we apply DC reverse bias here, and then that can cause the charge distribution with this region. But now we consider, we apply the VR plus dVR. So this will cause sometimes extension for our width, sometimes decrease for our charge distribution width, because of this AC signal is a dynamic. Sometimes in the that will cause an increase, sometimes will cause a decrease. So let's look at the text here. A capacitance is associated with the PN junction due to the separation of positive and negative charge in the depletion region. So as long as we have the separate of the positive and negative charge in this depletion region, that can cause the capacitance. And now we consider the AC signal. So the AC bias will lead to an increase in the reverse bias voltage dVR, and this will uncover additional positive charge in the N region and an additional negative charge in the P region as well. So that's something we have already described here, and therefore we can consider the capacitance can be estimated by dQ prime over dVR. That's the basic definition from the capacitance, where is the additional charge versus the bias. And then we consider this equation, then also this dQ prime, this one will still fulfill the charge balance. So that means that the charge here will be equal to the charge here, and therefore this equation still valid with considering the additional dqn and dqp here. And then we have previous derived xn. So in the end, we can have the formula to estimate the junction capacitance, which everything that's based on the equation we already have, just additional consideration here due to the AC bias. And this formula might not be immediately important for everyone who understands the semiconductor, but it's very important in the case when you do the electrical characterization for the measurement, because sometimes we are very often to use the capacitance, this kind of measurement, to understand our device physics or to understand our certain concentration or certain specific reason. So we are very often to try to characterize the capacitance, and at that moment, once it's needed to being characterized the capacitance, you will realize that this concept with DC bias plus the small additional AC bias is pretty useful and it's pretty important. Okay, so another case that we will want to introduce is what we call the one-sided junction. And this is a case that particularly considering the special case. This is a case we call the one-sided junction with our NA is much larger than ND, and therefore our depletion width in the P region will be much smaller than the N region. So this is a case that we discussed. Actually, we already discussed before, but now we try to remind it again. This is exactly a case where we consider the PN junction, but now we have the highly doped P-type versus just regular N-type. So this is a condition mentioned here. We have the highly doped P-type compared to the N-type. So that's a P++ versus N. And then we have already knew from the previous derived equation that if our NA is much larger than ND, then our XP will much smaller than XN. So the XP is a depletion width in the P region versus a depletion region in the N region. So since now the XP is much smaller than XN, so very straightforward, we can make this simplification that our total depletion width, which is XP plus XN, will be equal to XN, right? So I think that's a very a concept that is very easily to be understood. So that's we call this special case as a one-sided junction, because now the every depletion region width is dominated by the low doping region, which is XN here. So now we have this equation, and then now our W will be approximately as like the SN. So we can start to reform the previous calculate the capacitance equation, reform the previous derived equation as here showing here, and based on this equation we can make the linear plot where our y-axis will be the 1 over c squared. And our axis will be the VR here. So by considering this plotting, we can make a straight line where the slope is equal to 2 over Q x on S N D. So this is a doping concentration for the N region, and also the intercept in the x-axis is become minus VBI. So now probably you can see that the powerful of this analysis regarding for the one-side junction or the capacitance in the end give a way to extrapolate the doping concentration, also the building voltage. Of course, in the previous lecture, we have discussed the normal way to calculate the building voltage. But the problem is that that's under the assumption that you already knew the doping concentration. But sometimes the doping concentration is unknown because the doping concentration can be varied by the your substrate quality, your implant activation. Sometimes it's just not as a expected value that we can put in the beginning. Sometimes it will highly vary with the different substrate and also the process here. So then we can simply fabricate this kind of device where we consider a kind of the junction that we have the N substrate, and on top of N substrate we intentionally to have the P++ region. So if we consider this structure, this is actually a structure in reality very similar to this one, because if you look at the cross section of this one, P++ versus N, that's exactly considered as the same like here. But of course, in real fabrication, we will never be able to fabricate a device like in this way. It's always have the first substrate and we do some implantation. So the only way to fabricate the PN junction will be look like in this way. So with using this structure, and then we measure our junction capacitance. Then we plot the junction capacitance 1 over C squared versus VR. Then the purpose is that we can determine our ND, which is here. So that's the main purpose why we have to consider the junction capacitance, because of that gives a way to estimate the doping, because sometimes you should be not easily believe the substrate doping from the company, because sometimes it might difference due to the process or due to the certain substrate quality, and therefore we can use this simple way with a simple testing structure like this way, and finally we can electrically determine the ND as shown here. Okay, so the next additional concept is right now we are talking about some non-ideal effect, but the most of the semiconductor issues or challenges are mainly due to these non-ideal effect. The one of the most important non-ideal effects in the PN junction is that we have what we call the junction breakdown. So as we already shown in previous slide, if we consider as a current versus the voltage in the one PN junction and under the reverse bias, ideally we won't have any current, or the current will be extremely small. But it will be interesting if you try to increase the VR as larger as we can. But now if we increase the VR as larger as we can, then we can start to observe the leakage current start to increase. Then in the end, we will normally to have such characteristics that after certain large of our VR, the current increase dramatically, and this is a voltage that we define as a breakdown voltage. And this is a voltage that will completely destroy our device. And then after we see such breakdown voltage characteristic, normally that suggests that our device is completely failed, broken. We cannot use this device anymore. So the breakdown voltage becomes one of the key limitation for all kinds of semiconductor device. We should be very careful that our device should be operate below the breakdown voltage, because otherwise, once our bias is larger than our breakdown voltage, our device are completely broken, cannot be used anymore. So the reverse bias may not increase without limit. At some particular voltage, the reverse bias current will increase rapidly, and the applied voltage at this point is we call as a breakdown voltage. So now we have to understand what is actually the mechanism leading to this breakdown voltage. And the first mechanism is how we call as a Zener effect. And Zener effect is because of there's a particular breakdown that we call the Zener breakdown. And this is happening mainly due to the highly doped PN junction. That means if we consider as a PN junction in this way, and now we consider as a particular important case where we have the P++ versus N++ here. And as we already knew from the equation that our depletion width is inverse proportional to our doping concentration. So that means the highly doped always lead to the very smaller depletion width. And this smaller depletion width that will cause that the carrier can have such tunneling mechanism, can easily across this depletion width and reach to the other side. In a highly doped junction, the conduction and valence band on the opposite side of the junction are sufficiently close during the reverse bias, and therefore electron can tunnel directly from the valence band on the P side into the conduction band on the N side. So therefore, we can easily expect that there's a tunneling mechanism can be happen. And with considering this tunneling mechanism, that's why that once we consider for the xenon diode that has both very high, extremely high P-type and N-type doping that can cause this xenon breakdown. So that's one mechanism that can lead to the junction breakdown. However, the second one is getting more important than the first one because, to be honest, we will try to design the junction that has both highly doped in the P side and N side simultaneously. So we will try to avoid this situation. But in next, for the average breakdown, it's something that can be happen in the regular p-n junction. Even the doping is in the regular level here. So the average breakdown occurs when electron and hole pairs, electron and holes, moving across the space charge region. And because now we consider in the case that we apply the large electric field, large reverse bias. So this large reverse bias will provide a sufficient energy to our carriers. So our carrier can create electron hole pairs because of the carrier movement will colliding with some atomic electron. And once the carriers traveling and then try to collide with other electron, in the end, this carrier might start to break this the lattice, the bonding inside the lattice, and in the end, once bonding is broken, then we can expect that there are lots of electron hole pairs can created. So this is an example that first of all, we have the electrons being injected to this depletion width, and then because of this is under the the high electric field, high reverse bias, so this electron can start to, this is a high energy electron, the high energy electron can break silicon bonding. High energy electron can break the silicon bonding, and therefore we can expect that once the bonding is broken, then we will foresee there are lots of a generation of the electron hole pair. So now we have additional holes being generated and additional electrons being generated, and this additional electron also will receive a sufficient energy to break another silicon bonding, and also this process will be repeated again, will start to generate additional electron and holes here. So in the end, there are many electron and hole pairs, and therefore this is what we call the avalanche process. So this will become the average process. So that's the one of the very well known mechanisms that can lead to the breakdown. So the newly created electron and holes move in the opposite direction due to the electric field, and therefore this will create the reverse bias current. And the newly generated electron and holes may acquire sufficient energy again, and thus can cause the avalanche process. So for most of p-n junction, the dominant breakdown mechanism will be the avalanche effect. So for the every p-n junction we will see in the semiconductor, the dominant breakdown mechanism will be mainly due to the avalanche breakdown. And here is some more analytical calculation. So we can also try to consider the previous process as a certain equation, and then we might be able to understand that what would be the critical criteria that in the end can trigger this avalanche breakdown. So now we consider that the electron current with respect to the W, here this is W, so that we consider that our electron current ion in any place of X, but once we have this is initial electron current and start electron beams injected to the space charge region, and you start to have the electron hole pair generated. So then we can see our electron current is gradually increase, and once reach to the other side, that's what we call the ion W. So now we can consider in the end the total the current in the W location with respect to the current compared to the initial location has one multiplication factor that we call the Mn. So the concept is quite straightforward. We just consider in the end our INW should be certain correlation, but this correlation will times Mn, and then the Mn is a multiplication factor that try to represent the average results inside this space charge region here. Then we do a small mathematical trick that we do a derivative of the ion dx can be considered as this one, ion x alpha n dn dx. IPX alpha p d x, because of the total current in the end of inside this region for a small x location should consider the total current is combined as a contribution coming from the electron and holes, where alpha n and alpha p are electron and hole ionization rate that considered in here. So with this calculation, we can start to consider the following equation, and then we consider the alpha n is equal to alpha p is equal to alpha, and then we can have this formula. So this formula tells us that the condition where the M, once our Mn approach to infinite. So this is a case we consider for the average because we have the infinite multiplication that in the end we create the lots of the hole, electron hole. So we consider the Mn approach to the infinite. Then that means this one will be equal to 1. So in the end, once we consider the alpha ionization for carrier integration inside the x location from the x equal to 0 to x equal to w equal to 1, we can consider this is analytical criteria that trigger the average breakdown. And why we have to spend the time to talk about this? Because as you can see that this equation usually is not equation that the human being can be solved, because of alpha is sometimes not the simple value. It's a value that with respect to the distance and certain carrier type. So this for sure, this is the equation not used for us to be used for calculation. But this equation is very important for the simulation. If you have experience or in the future you will be involved in trying to use a simulation tool to understand the electrical characteristic for your semiconductor device, then you have to put a lot of equation inside the TK simulation software. And this TK simulation software, because it's run by the computer, so they can solve, they can do the lots of iteration, try to find the best condition. And then if you try to look at what actually the equation inside the simulation tool to identify the average breakdown current or average breakdown criteria, is actually exactly they just use this equation in our some simulation tool that can try to help us to simulate the average breakdown mechanism. So that's the purpose of why we have to understand this equation. We don't really need to calculate by our hands because it's not possible. But however, this equation is very important for the computer, for the TK simulation. Okay, of course, in the previous case we discussed that many different kind of the junction, and then for sure that we can still consider the non-uniform dope junction. So one possibility is that we call the linear gradient junction. So linear gradient junction, that means that this P region is not a constant concentration. The P region has a concentration with respect to the distance. So we have the ND, where is the N type, and then we can also consider that the NA in the P type can be varied by the distance, can have the distance dependency. So the one possibility is we can consider the linear distribution here. So for sure, this linear distribution can be still follow our previous way to estimate the rest of things, to estimate the doping, to estimate the depletion width, to estimate the building potential, and in the end, to estimate every characteristic related to the PN junction. So then we won't talk too much in detail, just for your reference that it is possible to have the doping concentration not is constant in the PN junction. In the end, we can still estimate the charge distribution, and once we have a charge distribution, we can still use the Poisson equation to estimate the electric field. So that's the same methodology that we used before, but just now we have to consider different doping concentration and different charge distribution. So this just for your information, so we won't spend the time to derive again because it's just mainly related to the mathematical equation, but the physics meaning actually is not that different compared to others. Of course, now you can see the building potential now can be highly depends on the x0. So that means that this is the initial position. And also similarly, we can follow the same methodology and then we can estimate the junction capacitance. In the end, we have this kind of junction, we can have the one particular equation for the junction capacitance for this kind of a junction. And last, just want to also provide the one possibility that we can generalize the N-type of doping concentration, but now we consider that our doping has this kind of the relation, and then we call this when the M is negative, we call this is a hyper-abrupt junction. So by consider this case, we can similarly still have the equation for the junction capacitance. In here, we won't talk too much detail because this is a very specific case that is being used as a variegated diodes. So the variegated diode is it's a very unique diode, and it's not diode that everyone will use, but at least you know that if in the future you will start to deal with this kind of diode, then you can come back to look at the textbook to understand that is mainly related to we have a different kind of the concentration in the PN junction. So in anyhow, this is all related to the non-uniform dope junctions. Okay, so finally, we spent the more than half of the semester is mainly talk about the physics, all the fundamental physics, but this fundamental physics will help us to understand the device behavior. So we have been already discussed the quantum mechanics. We discussed how the carrier can be transported in the piece of a semiconductor, and therefore we also talk about the factor that will contribute for the current, which is the diffusion and drift. And also we talk about the case that once we have the additional excess carrier and how this excess carrier will behave with respect to the time and the location. So in the end, once we have all these fundamental knowledge, that's enough for us to start to deal with the real device. And then the first device that we will talk about is a PN diode. This is easily understood because we just finished the PN junction, and in the PN junction, we mainly talk about the physics happening between the P and N. But the PN diode, we will start to try to understand the current versus the voltage behavior. So, therefore, the first question that we will be interested in is about how to understand the current flowing inside the PN junction. So we have several different cases that we have already talked about. The first one is under zero bias. So we all know under the zero bias, we have the Fermi energy, as shown here. That's our EF. And because of this is under the 0 bias, so the Fermi level will be constant through the older system. But now we have our Venn diagram will be roughly look like in this way, because the left hand side is a P type and then the right hand side is a N type. So that's a EC, EV, and then we have the built-in VBI voltage. That's a barrier between the P and N. That's a purpose to stop the diffusion current here. So this is something we already knew from the last chapter here. And this also relate to, if you try to picture our current IA versus our VA. So that's a current versus a voltage characteristic. So first one, the 0 bias, is a condition we consider here. Then for sure we can expect that there's no current because there's no bias. The bias is 0, but the reason why there's no current is because of we have these built-in barriers. So that's why your carrier cannot be easily flow to the left, to the right here. And then the second case, we will be interested in is under the reverse bias, and this is something that we also have already discussion in detail. In this case, our Fermi energy will be considered as a quasi Fermi energy here, where the left hand side is the EFP and the right hand side is the EFN. And we all knew that at this moment our VBI is not the pure VBI anymore. It's actually our band. The barrier between the left to the right junction will be increased, like in this way. And this is because now our VBI here, the barrier height will be equal to VBI plus VR. And because of this is the case that under the reverse bias. So we all knew that under the reverse bias, actually our diffusion width W is increased. And also, because of this large barrier height between the left and right, so there's no chance that this carrier can be flow. This is not possible. That's why in ideal case, if you try to look at the reverse current characteristic as shown here, and therefore the current should be close to the 0. And this is a case we consider once our VR is equal to V minus VA. So this is a case of the reverse. So this is the case of the reverse bias. And also, in the case of the forward bias, we can expect that this should be the case that our VB, the barrier between P and N should be decreased. So therefore, our PN junction, the first one, as similar, we will draw our quasi-Fermi level EFP and EFN, which will be here. And now our band diagram will be look like in this way, and our barrier height here is become VBI minus VA. So this is a case, sorry, this should be the positive in the anode side, so that's a VA. So this is a case we call as a forward bias. And now we can expect the barrier is reduced. What does that mean? So this means that the carrier finally can easily travel to the left. And also this suggests not only for the electron but also for the holes can be easily travel to the right. So now if you try to look at the forward IV characteristic, once we apply larger than certain voltage, we start to see the current increase. So this is a case under the forward region, and at this moment we apply the V forward is equal to VA here. But there's one particular voltage that I need to mention is this one. Similar to our transistor, although we haven't talked about MOSFET yet, but probably we already shown that in the transistor, in the MOSFET, there's a voltage that we call the threshold voltage. So that means we need to apply larger than threshold voltage in the end to induce the current. And similarly, in the diode, we have a same kind of voltage that we call it has a different name. Sometimes we call the turn on voltage, VT. This is also the name that being very often used. Sometimes we call the forward voltage drop. Sometimes we call the turn on voltage. But anyhow, it's just a voltage that we need to apply larger than this voltage. Then finally we start to have the current flow to inside this PN junction. So these three regions in the end create this full IV characteristic. See. So let's go through the text together. So there will be the diffusion of holes from P across space charge region where they will flow to the N region. Similarly, there will be the diffusion of electron across the space charge region, flow into P region. And in the end, this flow of the charge generates current through the PN junction. So that's the reason why in the end, under the forward bias, we start to have the current flow inside these PN junctions because our barrier is reduced. The barrier reduced, and finally our carrier is being diffused to the other side. And for sure, this is a physics-based understanding, but as being the engineer, we are not hope to have the physics-based understanding. We want to have the analytical equation to support our physics-based understanding. So the next question is that we would like to start to derive the equation that can help us to illustrate this forward turn-on current. So here is some of the assumptions we needed that once we try to derive the ideal current voltage relationship. And the first assumption is that we consider the absorbed depletion layer. So because of this absorbed depletion layer, and then that means our deep space charge region have the absorbed boundaries, and then semiconductor is neutral outside of the depletion region. So that's the first assumption. And the second one, we consider the Maxwell-Boltzmann. We consider the Maxwell-Boltzmann approximation, and that's we apply to the carrier statistic. And the third one is we also consider only the low injection case, and also the complete ionization. So in the previous lecture, we talked about lots of non-ideal effects. We talked about high-level injection. We talked about sometimes there's a non-complete ionization. There's a partial ionization. But in here, to simplify the case, we consider everything is in the perfect. That means it's a low injection, it's a complete ionization, and also the total current is a constant throughout the PN structure here, and the individual electron hole current are continuous functions through the PN structure, and individual electron hole current are constant throughout the depletion region. So these are the assumptions that we need to try to derive the ideal IV characteristic. And here is some more additional terms that we will use for the later calculation here. So we have the NA, ND, that's a pretty often used, and now we have the N0 here, which is a thermal equilibrium. Majority carrier in the N region, and we have the PM0. This is also thermal equilibrium. We have NP0. This is thermal equilibrium. But actually, this should be the minority carrier. And we have this one is also the minority carrier. So what this term means that if we consider a piece of the PN junction where the majority in the P side is a PP0, and the majority the N side is a NN0, and then the minority in the P side, which is a NP0, and then the minority in the N side is a PN0. The term is easily being confused, but if you just try to think about this, I think that should be still can be understood. Just as the term in the beginning is relative confusing. And okay, so the next one is we start to look at the equation from the beginning of equation we have. So we already have this equation for the built-in voltage. Now we can rewrite this equation as shown here. And now this will be equal to, this one is equal to the majority carrier, which is N0. And this one is a minority carrier, which is NP0. This is because of in the case of equilibrium, your N times P is always equal to the Ni squared. So we can transform this one become as a NP0, which in the end, this one is equal to exponential minus EVBI over KT. And now we consider the complete ionization, so our NN0 is equal to ND. So finally, we have this one, NP0 is equal to Ni squared over ND. Oh no, Na, sorry. And also, now our NP0 will be equal to NN0 exponential minus VBI over KT. And this is because you try to shift this to the right, and then you have this equation here. So now we can start to understand the minority carrier concentration, which is this one, on the P side junction to the majority carrier concentration on the N side has this kind of a correlation. So this is a minority carrier on the P side versus the majority carrier on the N side. So now again, I know that's very confusing because of if you try to, the term, the denotation here is already confusing, but the text here is sometimes very confusing. But in the end, what this equation try to express is that you have this kind of N and P junction, and then now we have the NP0 in here, and we have the NN0 in here. Sorry, this is should be the, this should be the left, should be the P, right should be the N here. So try to, this equation just try to derive the correlation between this is a minority carrier in the P side, this is a majority carrier in the N side. Try to find the correlation in the majority carrier here and minority carrier here. So now with this equation, we can further move on. Consider the case that now we consider is under the forward bias. So in the case of forward bias, we don't consider the pure VBI anymore. We consider VBI minus VA, right? This is because of this band diagram. We all knew the left, this is EF N, this is EF P. So in this case, this is EFP, this is EFN. So in this case, our band diagram become P-type. And then the difference between the EFA and EFP and EFN is our applied forward voltage, and therefore the built-in voltage right now become EVBI minus VA here. So that's why this will be here. So this is the case under the forward bias. And we consider this equation, we can start to separate this one times this one, which will become here. And also, this one can be considered as a NP NP is equal to NP0 exponential EVA over KT. This is because of this formula here. And also we consider this one is equal to this one. So finally, we have the NP is equal to NP0 exponential EVA over KT. And similarly, we have the PN is equal to PN0 exponential EVA over KT. So we have this equation to calculate the NP and PN. So with this equation, so the next is that we need to consider the location dependency here. So with considering the PN junction here, we have the P and N. And then in the middle, we have the PN junction, and also we have the depletion width here. So now we have to try to define the boundary in the depletion region. So if you try to plot the along the X space, and then this is a region for the PN junction, and also we can have the region at the x equal to XA and x equal to minus XP, and then in the middle is x equal to 0 here. And also we all knew that let's start to look at out of the space charge region in here we have the concentration. If you look at the minority carrier concentration in the P region, which is NP0. So the NP0, just a reminder again, is here. This is NP0. So we consider the minority carrier concentration in the P region. So that's the NP0. And similarly, we will consider the minority carrier concentration in the N region. So that will be the PN0. So now we also have the equation where we derived before that at the region of this one, we have the NP at the minus XP is equal to NP0 exponential EVA over KT. So this is the equation we have from the previous, this one. So this is the equation in the boundary at the x equal to minus XP. And also we have this one, which we also derived previously. That's a PNXN is equal to PN0 exponential EVA over KT. So that's at the boundary of the depletion region for the minority carrier, which is NP, and also the minority carrier, which is the PN. And also just reminder that actually the difference between this and this is actually the concept we already mentioned, that's called as an excess minority. Excess minority. So therefore, the excess carrier concentration in the P region will be equal to delta NP is NP minus NP0. So finally, why we have to spend the time to discuss excess carrier, because in dealing with real situation of the PN junction, we also have to take into account of the excess minority. And also, the difference between this and this is excess minority. And therefore, this delta Pn is equal to Pn minus Pn0. But you might be curious at why there's excess carrier here. In the previous, when we talk about excess carriers, we discussed at the case of piece of semiconductor, you have additional light. You have additional light putting on our semiconductor, and this additional light will generate additional electron holes here. But here we don't consider the additional light, but why there's excess a carrier, and this is because of under the forward turn-on operation, there will be the carrier. The electron here is a majority, start being across to a depletion region and reach this side. But once electron reach this side, electron become as an additional excess minority carrier, become like here. So once electron coming here, actually electrons become as an additional excess carrier, and also electron is a minority carrier here. So this additional excess carrier is because of a electron injected from N side, and that would become excess minority in P side. So let's just think about this again. Under the 4 bias, what we already knew, of course, we already understand the answer. The answer is that you have the carriers flow to the left, you have the holes flow to the right, and in the end, that will contribute as a current. But the question will be, this electron from in the N side, once being injected to the P side, this electron will become as an excess minority carrier, because originally there's no this electron. So this electron are the additional electron, and once the electrons are in the P side, that this electron considered as a minority carrier. So this electron will become additional excess minority carriers, and also this hole will become additional excess minority carrier in the N region. So that's why we will have this additional excess carrier. This is a carrier that being injected from the N side. And similarly, why we have these excess holes, these holes injected from P side become excess minority in N side. So that's why we have this excess minority here. So this is the carriers transport under the forward bias, and then in the end, this carrier transport under forward bias will become the excess carrier on the other side. Sometimes this is difficult to understand in the beginning, but once you get involved more and more in the later and later, once you see the full picture, that will make you more easily understand the term, the methodology to analyze this behavior here. For example, the excess carrier. Excess carrier. In the previous case, we talked about the excess carrier under the piece of semiconductor. There's no p-n junction. There's just an additional carrier. But why we have to talk about excess carrier? Because in reality, it's more easily happening in the p-n junction has an excess carrier. So that's the purpose to understand this part. That's why in the previous lecture we have to discuss the excess carriers. Okay, so finally with this concept, then we have to back to the previous discussed for the n bipolar transport equation, because of when we talk about n bipolar is we consider the case that both have the electron and holes inside the material, and we want to understand the carrier transport. But now you can see under the forward bias, this is also the case that both have electron and holes being involved. So now we back again to use our n bipolar transport equation to try to calculate for excess minority carrier holes. First one, we just consider excess minority carrier holes in the N region. So, and then this is a full equation, and then the first term is related to this one. This is the equation, look like similar to the what we have been already shown before. So therefore, we don't have to describe this again. And then now we consider excess minority carrier holes. This is excess minority carrier hole concentration, and this is 1 in here. This is excess minority carrier hole concentration in the N region. So from this n bipolar transport equation describes the behavior of excess carrier as a function of the time and then the spatial coordinates. The time is related to the t here. This is related to the x here. So this is time. And this is related to the spatial location, related to space. So, of course, we always try to do some simplification. So now we consider the electric field is 0 in the neutral P and N region. So therefore, because of the electric field is is 0, so that means E is equal to 0 and G prime is equal to 0 because there's no additional generation. And we also consider the steady state where our additional excess carrier versus a time in the end will reach the steady state, will become the 0 here. So finally, this equation can be simplified as a two equation, which one is and this is the case when x larger than xm, and then the LP square is equal to this one. And also minus and where Ln square is equal to this one. Okay, today because I have some other meetings at 12, so I need to leave earlier. So we will start the class at today, and then just a reminder that we will have the midterm exam next week at the same location here. And then also I think the TA will come. Just try to distribute back to the grading homework. So if you have any question, please let me know. So we will see each other next week.